Trigonometry comes to us from the ancient Greeks, and the word trigonometry actually comes from three Greek words, trigonia and metron. Tri meaning three, gonia referring to sides, and metron meaning measure or measurement. So three-sided measurement, or the measurement of triangles. Let's begin our study with a little vocabulary here. Let's talk about angle first of all. Now, an angle in trigonometry is the opening between a couple of rays, and that's kind of a different kind of definition than you would find in geometry. In geometry we define an angle as a set of points, as the points composing these two rays that have this common endpoint. And the opening is actually referred to as the measure of the angle. But here in trigonometry we talk about the angle as the opening between the two rays. Okay, the rays are just like half lines, and they have a common endpoint here. That common endpoint is called the vertex of the angle. And in generating this opening between the two rays, we can think of an initial side and a terminal side. The initial side being a ray which is fixed, and a terminal side being one which kind of moves and rotates to a particular point and then stops, and then we have this terminal side idea. Well, as we study trigonometry and we look at angles, we're going to refer to angles mostly in standard position. Standard position is a position of an angle where the initial side lies along the x-axis, the positive x-axis, and the vertex is located at the origin of the coordinate plane. And that's just a real handy way for us to get into the study of angles. And so this terminal side can be generated up like this and way around over this way and so forth. And actually the terminal side can be generated in the other direction as well. And we say that there's a positiveness and negativeness associated with generating this terminal side in this direction or this direction. When we generate the terminal side by moving in this direction, however far, it's a positive measured angle. And if we generate that terminal side in this direction, it's a negative angle. And when we talk about positive and negative angles in this way, then we could have a couple of angles that have exactly the same terminal side. And angles that have the same terminal side are said to be coterminal. Now, there are a lot of ways of generating coterminal angles. If I have an angle like this, and notice that I'm in standard form here, that I'm thinking about the initial side here, and if this is the terminal side, then this angle is the same as another angle that would be generated in the same direction but clear around the circuit, you see, back to that same terminal side. So the two angles are coterminal. There's another way to get to this same terminal side, and it would be to start here and generate the angle in the negative direction and just back to that same position. So coterminal angles. Now we know that our coordinate plane is subdivided into four quadrants due to the x and y axes. That we have quadrant 1 here, quadrant 2, quadrant 3, quadrant 4. And it turns out that we can label angles according to the quadrants that they fall in. And if an angle falls into, or the terminal side happens to appear in our first quadrant, then the angle is said to be acute. Now generally we're thinking of angles generated in a more normal way. That is, this angle as being generated just kind of like that. You see the small opening right here for that angle, but at any rate it's an acute angle if the terminal side falls within the first quadrant. And if the terminal side falls within the second quadrant, then we have an obtuse angle. Well, there are a couple of ways of measuring angles, and we want to talk about those ways separately. One way is to measure angles in a unit called a radian, and another way is to use the idea of degree. Now, you may already be familiar with degree from previous studies, and possibly, maybe not, familiar with the idea of radian. But let's talk about each of those ideas, and then we'll kind of blend them together in a little bit. Imagine the vertex of an angle located at the center of a circle, and we're going to sort of turn an angle from within a circle to talk about this idea of radian. Now this angle generated with a vertex at the center of a circle is called a central angle. Now when we have an intercepted arc here in which the arc length is exactly the same as the radius of the circle, then the opening here is 1 radian. That's the definition of 1 radian. So the arc length is the same as 1 radius unit. So 1 radian is where the r, the radius, is equal to the arc length s. Now, radians then, theta in radians, this opening in number of radians, can be calculated by using the arc length. We just take the arc length, whatever it might be, you see, and divide by the radius unit, and then we have the number of radius units along the arc length, so we have the number of radians for the opening of the angle. A very interesting kind of relationship now is formed between sort of a linear measure and an angle opening kind of measure. They're just kind of directly related like this, and we're going to explore this idea a great deal in the future. But for right now, let's just understand that theta in radians can be found by taking arc length and dividing by the length of the radius. So we have the number of radians, you see, involved here. Now, what about the number of radians for the entire circle? Well, that's pretty easy to calculate because we have an arc length for the entire circle. It's the circumference of the circle. Now, we know that the circumference is pi times the diameter of the circle, but a diameter is just 2 times the radius. And so our formula becomes circumference is 2 pi r. Well, how many radius units do we have here? We have 2 pi times the radius, you see, for our circumference. So we have 2 pi radians as the angle for our full circle, or 1 full revolution. Now, that brings us to the idea, we can then go over to our notion of a coordinate plane, and let's see, if we're talking about an initial side here and a terminal side which goes all the way around to this very point, you see, then we have 1 full revolution, and therefore we have 0 radians or 2 pi radians for that kind of angle. Now, from there, we can talk about what kind of angle do we have to this point. Well, let's see. To this point, this would be 1/4 of a full revolution. 1/4 of 2 pi would be 2 pi over 4, or pi over 2. So this would be pi over 2 radians as the opening to that point. Then continuing over to this next point, gee, that would be another pi over 2 opening. Or we could say all the way over to here would be half of 2 pi, 2 pi over 2, you see, or pi radians for this opening. And then to this point, that would be, let's see, it would be pi over, it would be this pi plus another pi over 2. Well, it would be, let's see, here's a good way to think about it. Pi over 2, 2 pi over 2, 3 pi over 2. And then all the way around is 4 pi over 2, or simply 2 pi. Now, angles which fall, or whose terminal side is in our first quadrant, we know to be acute. So acute angles are 0 to pi over 2 radians in measure. And a right angle is exactly pi over 2 radians. And obtuse angles have terminal sides that fall in the second quadrant, and that means that in terms of radian measure, they are between pi over 2 and pi radians. A straight angle, now a straight angle is just an angle formed with a sort of the terminal side and initial sides going out in opposite directions, and no wonder it's called a straight angle for that reason. But a straight angle is exactly pi radians, and a full revolution would be 2 pi radians. Now, think about the notion of coterminal here. If I have an angle which is, oh, let's say, let me erase a little bit here, clean this up a little bit. I want to think about coterminal angles here a little bit. If I have an angle in here that is, oh, let's say pi over 6 radians, then think about how I can generate angles that are coterminal with this. See, I could generate this angle to this point, and then I could go to that point, and then I could go clear around again like this for a coterminal angle. So it would be the pi over 6 plus a full circuit, which is 2 pi. You see, so I could actually take pi over 6 and add 2 pi and get a coterminal angle. And in the other direction, I could say, well, from here, I could go back the other way. I could subtract 2 pi, you see, going back the other way, and get a coterminal angle as well. Let's make the calculation algebraically. So to find angles that are coterminal with an angle of pi over 6 radians, I would do this. I would say I'll take pi over 6, and I'll add 2 pi. Oops, 2 pi. And that gives me a coterminal angle. And if I want another one, I'll add another 2 pi and another 2 pi and so on, and I could generate them all day long. And generally we would collect these two. The common denominator is 6, so we would have, let's see, pi over 6 plus 12 pi over 6, or 13 pi over 6 if we want to make it into one fraction. And a way of generating the angle using a negative angle, you see it was pi over 6, and subtract 2 pi. You see, that's another angle which is coterminal with this angle of pi over 6. And again, the algebra is in it for finding the common denominator. Let's see, it's minus 12 pi over 6. So it turns out to be negative 11 pi over 6 as a coterminal angle. Complementary angles are positive angles whose total in radians is pi over 2. And supplementary angles are positive angles that total pi radians. So if we wanted to talk about the angle that is the complement of pi over 6, then here's what we would need to do. The complement of, and that just means that we're inventing two angles that are complementary, and we have one of them, and now we want the other one, and it's called the complement of this one. All right, so for the complement of pi over 6, and we know the total of the two angles must be pi over 2, so we take pi over 2 and subtract pi over 6, and we'll have the complement of that angle. All right, and let's see what we have here. I think the common denominator is 6, so we have 3 pi over 6 minus pi over 6 becomes 2 pi over 6, or pi over 3. So an angle of pi over 3 is the complement of the angle pi over 6, because together they total pi over 2. All right, and for the supplement of the angle of pi over 6, we would have to take, well, let's see, supplementary angles total pi, so we want to take that total and subtract the pi over 6. And again, we need a common denominator, so this is 6 pi over 6 minus pi over 6, which is 5 pi over 6 as the supplement of the angle pi over 6. The degree unit for measuring angles can be thought of or defined as 1/360th of a full circuit. That is a full revolution. If you think about taking our initial and terminal sides right here, and then leave the initial side here, but the terminal side just kind of rotate it all the way around until it lands right on our initial side, that's one full circuit or full revolution. And that's 360 degrees. Now, if that's one full revolution, then let's think about what it means to turn an angle like this and an angle like this and that kind of thing. Well, this is 1/4 of the coordinate plane, so 1/4 of 360 degrees would be a 90-degree angle when we turn an angle to that point. And then if we go another quarter, then we have turned an angle of 90 and 90, or 180 degrees. And then another 90 degrees would put us at this position of 270 degrees. And a full rotation would be, well, if we're talking about an angle whose terminal side and initial side are right there at the same spot, then we're either talking about a 0-degree angle or a 360-degree angle. Or if we continue to turn again and again and again, it's 360 and 360 and 360. You see, we could just keep adding 360s if we want to describe angles that are just right here. And we could subtract 360. You see, we could go in the negative direction to generate angles to that point as well. Well, let's think about the notion of acute and obtuse here especially. We know that acute angles are angles that have a terminal side that fall in the first quadrant. And if we're measuring in degrees then an acute angle would be an angle between 0 degrees and 90 degrees. And a right angle is an angle of exactly 90 degrees. And an obtuse angle with the terminal side falling in the second quadrant, would be an angle between 90 degrees and 180 degrees. And once we get to this point of exactly 180 degrees for our angle, which we're showing here, we have what's called a straight angle for obvious reasons, I think. And the full revolution, as we mentioned before, is 360 degrees. Well, coterminal angles can be described in a number of ways. Let's think about an angle which is, let's say in the first quadrant of, 30 degrees. And let's think about generating angles coterminal with this angle. Now, one way to do that is to generate an angle from here and then go to this point, but then continue all the way around another full revolution, you see. So it would be this 30 degrees plus another 360 degrees. And another way to do it would be to maybe go to that terminal side and then go back the other way, all the way around the circle. So it would be 30 minus 360. Now, algebraically, we would do the calculation like this. If we want to calculate angles coterminal with an angle theta of 30 degrees, then we could say it's 30 degrees plus 360 degrees, or a 390 degree angle would be coterminal with that one. And another one would be, well, let's take this angle and add 360 degrees, you see, and we would have another coterminal angle. And in the negative direction, it's take the 30 degree angle, whatever the given angle is, it doesn't have to be 30, it can be whatever is given, and subtract 360 degrees. So an angle of negative 330 degrees would be coterminal with that 30 degree angle. Let's verify that over here. It's like we're taking an angle, and here's our initial side, and we're generating it in this direction, you see, all the way to this point, and that's negative 330 degrees. So it's coterminal with that 30 degree angle. So that's the idea. Now, we have a name for pairs of angles that total 90 degrees, and it's called complementary. Complementary angles are positive angles, that is, positive degree measured angles, that total 90 degrees. And supplementary angles are positive degree measured angles that total 180 degrees. So complementary and supplementary. Suppose we want to calculate the complement of the 30 degree angle. Well, the complementary angles are angles that total 90 degrees. So the complement of a 30 degree angle would be found by taking the 90 degrees for the total, you see, and subtract the angle that we already have, and we would find that the complement of the 30 degree angle is a 60 degree angle. So 60 degree angle and a 30 degree angle are complementary. That's the idea. All of those things mean pretty much the same stuff. For supplementary, I can generate the supplement of a 30 degree angle by taking 180 degrees and subtracting 30 degrees to find that the supplement of the 30 degree angle is a 150 degree angle because the sum of the measures of these angles is 180 degrees. That's what makes them supplements. Now, sometimes more accuracy is needed than just the single degree, and it's for that reason that degree measured angles are divided into smaller units called minutes and seconds. Now, and the designation is this, that if we're talking about a very, very accurate measure here, it would be 22 degrees, 40 minutes, and 20 seconds. And the number of minutes is, well, let me say it like this. There are 60 minutes in a degree, and there are 60 seconds in a minute, just like with time between these two. So it's this 60 idea, 60 of these for that and 60 of those for this. You see, so we could have this kind of angle. Now, when we're actually using this information, though, a lot of times we have to convert this into a decimal form. And then sometimes we want to take a decimal form and convert into degrees, minutes, and seconds. Well, let's go through both of those calculations. Now, just to understand that we have 22 degrees here, and we want to just think about, in changing this to a decimal form, think about just rewriting this as some number of degrees here, degrees here, degrees here. Well, 40 minutes is really 40/60ths of a degree. You see, that's putting it into the degree idea. And then 20 seconds, well, let's see, 20 seconds is 20/60ths of a minute, but it's, and then there's 60 of those in this. So wow, let's see, a minute is, a second is 1/60th of a minute, but a minute is 1/60th of a degree. So 1/60th of 1/60th, that's 1 over 3,600, you see, of a degree. That's what each of those rascals are. So what we have to do here is say that this is 20 over 3,600 for the number of degrees that this is. And now you change this into decimal form with the calculator, and you find this to be 22.672222 and so on. But rounding to the nearest hundredth, it's this many degrees. Now let's go the other way. Suppose we have 135.125 degrees and we want to change this into degrees, minutes, and seconds. Think about it first by taking the sort of the whole numbered part of the decimal and separating it from the decimal part, from the fraction part. All right, so we have 135 degrees plus 0.125 degrees. But this 0.125 degrees can be thought of this way. Every degree is 60 minutes. So we can say, let's take this number of degrees and multiply times 1 minute, or excuse me, times 1 degree. And 1 degree is 60 minutes. So it's 60 minutes times 0.125. So that's 7.5 minutes. And now separate this. It's 7 minutes plus 0.5 minutes. Now a half of a minute, you see, is half of that 60 minutes, 60 seconds in a minute, so it's 0.5 times 60, or 30. So it's 135 degrees, 7 minutes, and 30 seconds. Let's establish a relationship between angles measured in degrees and angles measured in radians. It's pretty easy to do because we know that one full revolution in degrees is 360 and in radians it's 2 pi. So 360 degrees is equal to 2 pi radians. And then half of each of these means that 180 degrees is equal to pi radians. And half of that, 90 degrees, is equal to half of this, pi over 2 radians. And half of that, you see, half of 90 degrees is 45 degrees, so half of pi over 2 is pi over 4. So 45 degrees is equal to pi over 4. You see, and if we want to make a conversion from one to the other, then we could think, well, like 30 degrees. What's 30 degrees in radians? Well, we could think, well, 30 degrees is 1/3 of 90 degrees. And 90 degrees is equal to pi over 2. So if 1/3 of 90 degrees is 30 degrees, then 1/3 of pi over 2 must be the equivalent in radians. So 1/3 of pi over 2 is pi over 6. See, so that's one way to get at a conversion. But another way is to create a more general relationship, not dependent upon these integer values, you see, that we're going to have to divide or multiply or whatever. You know, sometimes the fractions are not convenient, as it was with the 1/3 here. But here's what we look at. This 180 degrees is equal to pi in radians. And we use that as the basis for a little proportion. That theta in degrees corresponds with 180 degrees in the same way as theta in radians corresponds with pi radians. And now with this little relationship, we can make conversions all day long. That is 30 degrees. Let's see, is how many radians? Well, let's see. 30 degrees corresponds with 180 degrees in the same way as theta in radians corresponds with pi. And now we solve this for theta. Well, let's see. It's pretty easy, I think. Multiplying by pi on both sides, you see we get 30 pi over 180. And then these go out, and 3 over 18, oh, that's 6, and so it's pi over 6. So it's pi over 6 radians. Let's go through it another time or two. How about 220 degrees for the number of radians? We want to convert here. So it's 220 degrees corresponds with 180 degrees in the same way as theta in radians corresponds with pi. And again, it's a matter of just, we could cross multiply here, but it's much easier just to multiply on both sides by pi. So theta, we find, is equal to, multiply by pi on both sides, and pi goes out over here. And over here it ends up in the numerator, so it's 220 pi over 180. And then divide by 10 on both sides, and then reduce a little bit because they're both even in numerator and denominator. 2 into 22 is 11, and 2 into 18 is 9. So 11 pi over 9 would be the number of radians we have. How about 3 pi over 2 radians and converting to some number of degrees? Well, again, it's the same idea. We take the number of radians and put it over pi, and then this is equal to theta in degrees over 180. You see, and again, we go through the cross multiplication thing. Now, very quickly, the pi's go out here, and we have 180 coming over here. See, multiply on both sides by 180, so we find theta in degrees equal to, now I'll just write the factors. This is 3 times 180 over 2. And now the 2 and the 180, let's see, this is 90, 3 times 9, so we have 270. So this is 270 degrees. Now, generally we've talked about radians by using the idea of pi, 3 pi over 2 and 2 pi and pi radians and so forth. We know the value of pi. We can approximate it very easily with the calculator and so forth. But it's not always the case that we have to use pi when we describe radians. We could have 1 radian, for example, or 2 radians or something like that. Let's approximate the number of degrees in 2 radians. Well, again, we use the same idea. Now we want the number of degrees here. So it's 2 radians corresponds with pi in the same way as theta in degrees corresponds with 180. So let's see, multiply by 180 on both sides. Gee, theta turns out to be 360 over pi. That's 360 divided by some approximation here. Using the calculator, we find that this is approximately 114.59 degrees. Here's how the correspondence between degree angles and radian measured angles comes in handy. Suppose we have a situation where along this circle we have an angle of 240 degrees generated, and we have a radius of the circle of 4 inches, and we'd like to know the length of this arc. You see, the length of this arc formed when we turn this angle of 240 degrees. Well, we understand from just by the nature of degree angles and radian angles that it's the radian angles that are related to arc length. So the first thing we need to do here is convert from 240 degrees into some number of radians. So let's go through that. 240 degrees corresponds with 180 in the same way as theta corresponds with pi. Multiply by pi on both sides, and we have 240 pi over 180. Reducing a little bit, we find theta to be 4 pi over 3. Now this is some number of radians. Well, now that we have the angle in radians, and I can emphasize that up here, I can say that this is then 4 pi, whoops, I want 4 pi over 3 in radians. Now we go back to our fundamental understanding of the relationship between the length of an arc and radian. That is, theta in radians is arc length over radius. And I suggest that you write the words out here. It's possible to write this as, well, arc length we usually use the letter S, and for radius we use R. But I don't want you to memorize a bunch of letters. I would like for you to understand a relationship that the angle opening is found by taking arc length and dividing by the radius. So you get the number of radius units you see in that arc length. And that tells you the number of items here for the radians of the angle. Okay. Now, what do we know about this? Well, we know that the theta, the angle here in radians is 4 pi over 3. We know the radius is 4. So multiplying on both sides by 4, we find the arc length to be 16 pi over 3, or approximately 16.76 inches.